Okay, I got a story for you to start our video today. I was talking with somebody who's kind of famous in privacy engineering, and they were trying to dunk on my work. And I was not really understanding what they didn't understand until we got to a point, and then the person's like, "Well, you're talking about information theory." And I was like, "Yes, I am." Then I realized, oh, most people don't understand information theory enough to actually do the privacy work that they should be doing. So today we're going to talk about information theory, and we're going to open it up for people so that they know when we're talking about advanced privacy engineering or pets, we're also talking about information theory, y'all. So it's all about the information, y'all. Let's move on. What are we trying to learn? When we're talking about machine learning, or really any advanced data problems, we're usually trying to learn something to predict. We might be trying to predict what happens next. We might be trying to recognize things in images so we can drive around them, right? So we can figure out how far is something, how near is something, and then drive around that. Or we might be trying to store the entire information of the world so that we can essentially do search and retrieval, which is at some level what these chatbots are doing. So these might be all of the different things that we're trying to learn. And no matter what we want to learn, we need information. And we usually find information in data. They're not the same thing. We're going to talk about that in a second. So we have data. That means we have digitalized and stored something. And in that data exists information. So training data for forecasting, we might take historical view of what's happening, and we might feed that in a time series way into something. We might have, if we're doing computer vision or if we're doing driving or anything where we're going to use a video or image to make a decision, we're going to want this training data with the labels of all of the different things in the images that we have, and maybe even extra information like how far do we think they are. And then for something like storing the information of the world, we might want to have a bunch of books. We might want to have the whole internet. We might want to have a bunch of videos that have been transcribed. We want a whole world of information that we then store in the model to some degree, right? So these are all things. And again, this is all the data that we collect, and we hope in the data there is enough information for us to learn. So what is information? Well, what we're talking about is Claude Shannon's information theory. And I want to try to give you an intuitive sense. We're not going to go into formulas or anything like this in this video. I'm sure you can find plenty of examples on blogs or the internet, or you can ask your favorite chatbot for more information. But I want to give you an idea of information. I want to particularly give you an idea of information related to learning. So let's talk about information. Here's you. You have a job. You're supposed to figure out what's the composition of all of the balls in this jar, right? We can see it, but you can't, right? Otherwise, you could just count. You want to try to do that as efficiently as possible. And so you're going to sample some of it, and then you're going to try to guess the rest based on what you sample. Seems reasonable. I'm sure that you've seen this problem before if you studied statistics or something like this. So, okay, you pull a ball. It's red. Okay, learned something. Information, learned something. All right, there's definitely red balls in there. Let's figure out how common they are. You pull another one. Oh, another red ball. Interesting. 2 out of 2 red balls. This second red ball has slightly less information. You're slightly less surprised that you pulled a red ball because you already knew that red balls were in there. Then you pull a third one. Now you're starting to be like, is the entire thing just full of red balls? Is that what we're doing here? And maybe you're starting to increase your confidence that you're going to see another red ball and decrease your confidence that you're going to see something other than a red ball. Then you pull a blue ball and you're like, where did that come from? And here we can see, again, that surprise moment, that aha moment of learning something new. That means information, right? And when we have most expected outcomes, we have less information. Perhaps in the beginning, it gives us more information, but over time, it gives us less information. And when we have least expected outcomes, we have the most information that we can learn. Perhaps we don't want to learn that information. That's fine. If it's super, super outlier, we might not care. We might not want to learn. But if we need to learn, like let's say for figuring out anomalous situations, or when our data set is not really representative of what we're trying to learn, then those really unique examples, they're going to be a lot of information compared to the other people around it or the other non-complex examples around it, right? And this then relates to privacy. So I want you to start thinking of this, especially when we have not completely accurate data, where data is not fully representative of our world, which is true with most of the data we collect. How does that relate to privacy? Well, what if you're the only example of a particular language or type of slang? If our goal is to learn this language, then you're going to be way overexposed because the information in your examples is way more than any other examples, right? What if you're the first example and you're in a pretty small population? Like if you're the first of those red balls, then you kind of just blend in with the crowd, right? But if you're the first of those blue balls, remember there was only like a few of those. Or if you're the green ball, right, there's only one of you, right? So again, if you're the first of a pretty small population, when we think about how we do machine learning, that initial updates of the weights is going to be heavily biased towards your information, your data. Let's take an example. Maybe that's relevant to some of you. Maybe you're a Leet coder. I know that's old internet speak, but 90s internet for the win. So let's say that you coded pretty much all of this like really popular library or something like that. How many repetitions of your code is going to be there, and how much information just from a numbers game of that particular type of library is going to be stored about you versus other people? And this is all, again, yes, 100% related to information theory. And privacy and information theory belong together, particularly when we're talking about machine learning. I can recommend you take a look at some work in the field, which has been around for more than a decade. What can we learn privately? Take a look at this paper, then look at papers that cite this paper. If you need tips on reading papers, I got a video coming up soon. So reading papers and starting to learn about how information theory and privacy and learning theory all relate together is going to make you a way better machine learning nerd engineer and a way better privacy nerd or engineer. So learn about learning theory. Learning about learning theory can teach us a lot of really cool stuff. And this is computational learning theory. So what problems are complex versus simple? And this again relates to information theory because complexity and information go together. What information lies in our data? So do we have enough information in the data that we're collecting to actually learn what we want to learn? This is important for us to think about, reason about, and also do something about. What information do we need in order to learn complex problems? So the more complex our problems get, or the learning tasks that we have, then the more information we need in order to learn them. Because again, it's harder to learn. It's harder to predict something that is just more difficult and complex in and of its nature, right? And this is why deep learning has really taken over a lot of the more complex problems versus the more simple problems. And when we learn about computational learning theory, it also deeply relates to fields like privacy and security. So AI privacy, AI security, or machine learning privacy and security. And this is because often in security, we're exploiting known versus unknown. So we're trying to enter unknown territory to get the model to give us a non-robust response. We're trying to increase model uncertainty to destabilize the behavior of the model or the outcome of the model, right? That's often what we do in security. It's not the only thing, but that's often what we do. And then when we're talking about privacy, we're again thinking of this sparse versus dense. So it's one aspect of many, but one way I want you to visualize it in your head is, do I have a lot of neighbors around me that protect my privacy, or am I kind of alone out there? Or am I sticking out in a weird way of my peers and neighbors? And that relates to my information relative the others around me, as well as the information and others around me relative to me. So both ways. And so when we think of this sparse versus dense, we're both talking about information, but also learning theory. You want to super nerd out and maybe not fully understand everything that's happening in the video, I highly recommend this video. I'll put it as a link. But I hope you got intrigued today about information theory, about computational learning theory, and about why it is, as privacy engineers, in my opinion, we should be talking more about information and less about other topics.